the in-cron tool suite editor window. And the editor window is where you enter your system model, where you describe the system that you want to analyze, and where you then start either the analysis using the validation from chronVAL, what we will do first, or you can start the simulation to simulate the dynamic behavior of the system. What we have here is the typical editor window of a system. We do not use Eclipse, as you might see, but we do consider that for a later future. We have architected our user interface in a way that we have wizards that we have on the left column here, a system wizard where you describe the system, a bit more architecture wizard. We have an entering window for the execution times and monitoring them. We have a part where we show the clocks, because that's an important part in an embedded system, that you have often varying clocks or you have periodic inputs from the outside that drift against the clock of your system. And we have the possibility to enter real-time requirements that we will show you in detail later on. And you have to have the possibility to stimulate your embedded system. And for the stimulation, we have specific stimulation editors. In this case, I've already loaded an example project file that I want to validate later on. We show a project or a system in a system tree view, and the main component first on the upmost level is a project, and under the project, the next most important part is a resource. So a resource, in this case, is a microcontroller, for example, but actually if you just think of something that is able to compute or do things in the embedded world, a bus system can also be seen as a resource. In this case, we have here a resource, a processor model. It's a generic model here, and it has only one core, but we are also able to show multi-core systems. Every resource comes with a scheduler, and actually it comes mostly with two schedulers, because most embedded systems have at the utmost priority an an interrupt service routine. So we show here the interrupt service routine scheduler, and within that schedule there's the operating system scheduler. In this case, it's a generic default scheduler. So we have another scheduler within this hierarchically shown. In the scheduler, or what does the scheduler do? The scheduler schedules processes or tasks or threads or whatever you normally name them in your operating system. We, being quite close to the automotive industry so far, we mostly call them tasks, and these green bubbles represent these tasks. We gave these tasks names that give you an idea what the cyclic period of these tasks are. So this one, for example, is repeated every 10 milliseconds. We see that's not only the name that is the 10 milliseconds, we also see that we have an execution time. In this case, the execution time we put here is 3.5 milliseconds, and that in the best and the worst case. The 10 millisecond cycle is actually not triggered by the operating system simply. It has here a connection, and this connection here is an activation. This activation comes from the T10 milliseconds activation here, so this is an activation source. So we have in our project also activation sources that you can think of kind of interrupt resources, but we will see later on that we have even an interrupt source as an activation source specifically in the system model. So we have here something that triggers every 10 milliseconds with no jitter and no minimum separation distance every 10 milliseconds, and this source is linked to the 10 millisecond task down here, so we see how it is scheduled, how it is triggered. So what does the overall system do? It triggers all these tasks with different periods and time, and now we want to know what will be the scheduling in the worst and best case. When I start the validation, the system will be undergone a mathematical analysis, and we're now looking for the worst case phase shift and stimulation of the overall system to show the worst case and best case response times for these processes or tasks. The mathematical analysis is now completed, and it shows two windows. chronVAL has two windows to show how the system in worst and best case will react. the most easy one to understand might be the response times showing in bars. So what we show here is that you have these bars for every process that you have in your system, and the length of the bars depicts the worst case response time for the thick bars, and the thin bars, it's the best case response time. So if we take a look at the 200 millisecond response time here, we see that it has a portion of 12 milliseconds running, and actually it's 37.5 milliseconds preempted by higher priority tasks. We can take a look at this in detail when we open up the probe for the 200 millisecond task, and here we can see that it is preempted for 37.5 milliseconds by a portion of 20 milliseconds from the task 170 milliseconds, and a portion of 17.5 milliseconds by the 10 millisecond tasks. And their own worst case execution time is 12 milliseconds. Another view, and this is maybe a bit difficult in the first point to understand, but once engineers have been using this event spectrum viewer, they get a very good idea of the overall timing of the system, and especially what performance reserves they have in their system is the event spectrum viewer. And the important part here to understand is that we have a delta t on the x-axis. So we don't show here the time, how it is processes on the x-axis. We show rising time intervals. So if I take a look here at the 200 millisecond task here, and let's say what's the maximum computation time of the 200 millisecond task here, we see actually a kind of a step of a ladder or stairs here. And what does this show? If I zoom in a bit, it shows that in an interval of 200 milliseconds, or a bit lower than 200 milliseconds, there will be maximum the request for a computation time of 12 milliseconds here. And minimum at 200 milliseconds, there will be the next request for computation time, and it will request another 12 milliseconds, so we're here at 24 milliseconds computation time. So for example, if we say we have a 900 millisecond window, any time window for 900 millisecond length, what's the computation time the process will have a worst case requested? Then we go up here and see that its worst case is 60 milliseconds operating time it requests from the resource. But since the 200 millisecond task is not the only one who is running on the system, we can see what, for example, is the minimum available capacity for this task. So if I go back with the zoom, we see now a red line, and this red line depicts what is the minimum available processing time that the higher priority tasks that are also defined in the system leave for the 200 millisecond task. So whenever we see a vertical gap here, we see that the 200 millisecond task could use way more computation power, so there's still some error here for this. So you could, for example, add more functionality into the 200 millisecond task. There would still be enough computation time remaining to complete this. But that might be a problem for more and lower priority tasks like the 2000 or 500 millisecond task here. I do not want to go into too much detail here on this display. It really takes a bit more explanation that I can show you, but it's really very helpful if you, for example, have a system under development and you are the architect and you want to see, okay, what would happen if this or that task has a higher load? Will there still be guaranteed enough computation time left for my system? So you can easily see where you could map some more functionality if it's into the 200 or 500 millisecond task, for example. Now, the worst case response times we have here have not been checked against any requirements. So let's see how we could enter a requirement. We can say that we go back to the editor window and say that, let's say we have a requirement. We want to not allow any RTOS errors in our system, and I want to add another requirement. I want to add a response time requirement. And the list that you see here is just an overview of what types or classes of requirements we currently have integrated here. We are working on more of those, and it's a template-based system. So if you, for your own application, have specific requirements you would like to express here, it might be quite easy to implement for us, for you. Now, I said I'd like to have a 200 millisecond response time for the 200 millisecond task, a response time requirement, and let's say it shall complete in 45 milliseconds. That shall be our requirement here, and we say that's the response time 200 milliseconds. And if I start the analysis again, this response time will also be considered in the analysis. And after a while, this analysis takes a bit, but actually if you have other worst-case response time analysis methods, especially like rate monotonic analysis tools, you might be used to quite a long analysis time instead of this one. And now you see here that we have a requirement of 200 milliseconds and shown here as a deadline, so you immediately see that your deadline is not met here in the worst case of your system. Now, it could be interesting to see what was really the combination of the response, the activations of all processes in my system that led to exactly this worst case response time. What I can do, I can have a Gantt chart-like display to show me the, oops, no, sorry, I have to first go to the one that I want to watch. I can have a look at the worst case scenario that leads to this response time of the 200 millisecond task. It opens up a display that is a bit looking like a Gantt chart. It's the process state diagram that you will see in chronVAL later on. And now what we can see here is that we have the processes here in every row, and every time a process is not active or dead, it's the gray line in the bottom, or if the process is really running, we have the blue line on the top, or if the process is actually pushed back by the higher priority processes, we see that they show here a green line. So we, in this case, see that these processes here actually play a role in delaying the activation of our process 200 milliseconds, and we see here that we have a 49.5 millisecond response time. And this is one situation that would lead to this worst case response time. I'm making it a fine distinction between could be, because actually the worst case response scenario might be different, or there might be multiple scenarios that will lead to the worst case response. For example, if you just think of a slight phase shift between this and that process here, that would all lead to the same response time. So this is not the real worst case situation, it is a worst case situation that leads to the worst case response time. And you see that it is highlighted a bit in red as well, because it violated our requirement.